gonna have episode 14, Ionic Bonding. So, most of the bonding that we have talked about is not ionic. It is either covalent or hydrogen. So, today we're gonna talk about ionic bonding. The only element found in large amounts in nature are 4 precious metals: copper, silver, gold, and platinum. 6 noble gases: carbon, nitrogen, and oxygen, and sulfur. Most elements combine with one another as ionic salts. So when you hear the word salts, that means ionic. So once you hear the word salts, that means ionic. Now, we have seen how H and elements are bigger to form covalent. We will look at ionic. So this is mainly part of the D block and the S block and the F block. We're not going to get into the F block today, but we are going to get into the S block and D block. Which nucleus is the strongest, most positive? This is just a bit of review. Obviously, it's fluorine, then oxygen, then nitrogen, then carbon, and what's next? Well, then we have boron. We haven't talked a lot about that. And beryllium, not a lot about that. And lithium. Covalent bonds hold atoms together through shared pairs of electrons: hydrofluoric acid, water, ammonia, methane. But here we have boron. So you can see that instead of having the octet, 1, 2, 3, 4, 5, 6, 7, 8, we have the hextet. So it's sort of a violation. Yeah, a violation of the octet rule. It is not. Beryllium hydride. Oh my god. It's a quadratic. This is held on its outer electron. It is very hard to make it. Only scientists can make it through very hard ways. It's super duper hard to make beryllium hydride because beryllium is such a weak atom. Yeah. Remember that? Yeah. Such a weak atom. Yeah. And listen, the hydrogen steals electron fulfilling the helium configuration for both atoms. You can see back here whose protons is closer to the electron. Obviously, it's lithium. So you can see I've drawn it a lot farther to show that because it pulls out like that. Oh no, electron. This is like the opposite of a hydrogen bond, right? The element that pulls the hydrogen, but this time it's the hydrogen that pulls the element, sort of like the reverse hydrogen bond. Fancy word there. Okay, not very fancy, but still, yeah. And then these have a charge. The reasons they're negative and negatives and positives attract and therefore makes them attract. The reason they're negative, there has an extra electron. And this is positive because it's missing an electron. Lithium hydride is our first example of an ionic compound. Here it is. Hydride, how many protons, how many electrons? There's 1 and 2 electrons. Lithium, 3 and 2. So overall, negative because there's an extra electron, positive because there's an extra proton. And these attract, and LIH. Here we go, both fulfilling the helium configuration. Very dreamy. Okay, get back to chemistry. Then here's the 3D models of what we predicted it looks like. Now let's look about lithium fluoride. Okay. So, here we have lithium fluoride. You expect it to be shared, but lithium, the electrons are so far away that instead the electron goes to a better home. Here's an analogy. It's like, just say you have a bit of gas, but however you have to, let's just say like that you have a lot of cats and you just want another. You don't have enough time to keep care of one of your cats. Well, then you can ask another person to help keep care. In this case, these electrons as a cat, you're the one just giving the cat to the, and here we are, lithium fluoride. LIF both fulfill the helium and the neon configuration. And here's the electron count, positive and negatives. All positive and negative charge balance, giving a neutral compound. Though it cannot be neutral, and therefore you must add more. Yes, I said add more stuff to it. What about lithium oxide? Same thing, but this time we need 2 lithiums because oxygen needs 2 electrons, and still, this time we have Al2 as the notation. And now we have plus, -2. That's why we need 2 lithiums because you need 2 positives if you want to balance out 2 negatives. Lithium nitride. This time we need 3. Oh my god. Yeah, crazy. 2, 3. Here we go. And whoops, lithium nitride. Here's the notation. Well, we have the helium and neon configurations. More daydreaming. Yeah. This is what elements was for. Lithium nitride, we have 1 positive and 1 negative 3. 1, 2, 3. So, and therefore, we need 3 lithiums to balance the charge. Sort of like a game of bowling. For example, if you have 1 gram on the other, you need to have another 1 gram if you want to balance it. Like, use a balance scale. Let's say you have 1 gram of stuff. But then, if you want to balance out, you have to have another gram on the other side. One side to the positive side, one side to the negative side. What about sodium chloride? Oh, have you heard of it? Might have. Oh, sodium chloride. Here we go. And NaCl. Now, this is looking from the neon argon. It's salt. Your quick electron count has a positive charge, negative charge. So, if we go black over here, remember, hey, you might have noticed a trend here because if we go back to the periodic table over here at the beginning, over here, you may have realized that the S block forms a positive charge and the P block usually has negative charges, and that's true. Well, most of the time that's true. And the D block, F block, S block, positive charges, P block, negative charges. So that's how these things work. That's the pattern that you may have noticed here. Let me get back to through my slides. Over here. Where are they? Sorry. Okay, here we go. And this is the salt. What about magnesium chloride? Well, this time we need 2 chlorides. Because magnesium has 2 extra cats. Together we have MgCl2. MgCl does not exist. Okay? And here we have the configuration to a quick electron count, negative, positive 2, as you can clearly see here. What about magnesium sulfide? Here we go. Whee! MgS, neon argon, quick electron count, 2 plus 2 negative. What about potassium chloride? So, here we go. Argon configurations for both. And then do a quick electron count, positive, negatives, one extra proton, 1 extra electron. Protons are positively charged, electrons are negatively charged. What about calcium chloride? Ooh. Interesting, aren't they? Well, if we do the quick electrons, here we go. Calcium chloride, CaCl2. CaCl does not exist. You need that too because, well, calcium has a 2 plus charge. And calcium oxide. What about that? Now this is starting to look very funny, aren't they? Yes, that's right. Calcium oxide. Wow. Obviously, this is going to get very interesting. As here we go. You go like this, CaO, like this. Configuration is complete. Do a quick electron count, 2 plus 2 minus. And it's part of cement making and is known as burnt lime. What happened when we add water to calcium oxide? Water gives away a proton to oxide O2, creating 2 extra oxide O2 molecules. Wheezies. Ooh. Now this one's calcium hydroxide. Is part of cement making is known as slaked lime. C and CO2 are part of the cement making, but after water, cement is the most used material on earth. Cement is used to make concrete. We'll talk about that in the next episode. So, here's titanium dioxide. Oh, remember those d electrons? Those d electrons. we have 2, but what about these extra 2 electrons? Oh dear. We have another one because we have to complete it. It's more stable like this. So titanium is TiDO2 like this instead of TiO. Here it is. The configuration is due to collection current. This thing lost 4 protons. This thing has a -2. What about vanadium oxide? Ooh, remember? 2. Okay, here we have. And then, well, we have these extra 3 electrons, so we gave them 2. But what about this remaining electron? What do we do with it? We get another vanadium? Oh yeah, are you insane? No, we are not being insane, guys. This is truly because you need another set. Here we go, and then, oopsies. Here we go, here we go. Now, this is complete for everyone. 2 vanadiums and 5 oxygens. This is called vanadium pentoxide, by the way, if you're curious. Vanadium pentoxide. Oh my god, all of these plus 5, and oh my god, it gets complicated if you have more things. Oh my god, and together these are called minerals. We'll talk about those in the next episode, though. My goodness. Zinc oxide. Actually, this tends to be stable. We have because remember, this is called the pseudo-electron configuration, so it's noble gas-like. So we can do this completely fill d orbital, zinc and neon configurations. Do quick collection action, 2 plus 2 minus. What about iron oxide? There's 2 ways. We could do this, which looks incomplete to you. What do you think will happen now? What do you think will happen now? Because, well, here, let's think. Take away 6 electrons. Oh, that's way too much things to take away. 1, 2, 3, 4, 5, 6, unlucky. Add 4 electrons. That's not a good idea because the P block, remember, always has a positive charge. Everything except the P block has a positive charge. There you go. Nothing? Well, not very complete. Take away 1 electron. Yes, it's nothing. Yes. FeO is stable set even though iron has a partially filled orbital. FeO, 2 plus 2 minus. Add 4 electrons. No, come on. 2 of the electrons would actually be used to fill the empty 4th orbitals again. Yeah. And what you do is you just do this. Take away 6 electrons. This could be a very positive charge ion, which is usually not favored. Take away 1 electron could work if you have another. But then, yeah, that's a stable configuration. But for the oxygen, oh shoot, we need much more than just this. Here we go. Plus 3, plus 3, negative 2. This is iron oxide. And here we go. For iron, this is called iron. Simple rules like do not apply, but more about how deep hardening for the metal atoms. So here, iron 3 because it has a 3 plus. Iron 2 we use Roman numerals, and here's a plus 2. Look at these amino acids. What do you see? Let's look at asparagine. Amino acids for harmonic interactions with dissolved ions. But here they are. Whoa, sodium thermochlorate. Remember that? Wow, there's a nodium. Wow. DNA, oh no, so many negative charges. How is I supposed to deal with this? No worries. Magnesiums. Oh my god, DNA has a lot of magnesium and negatives. This makes it neutral. But also balanced by. Now let's look at this. What about these two? This osmium glutamate and negative charge and can form a side bridge with the serotonin which is positive charged. So here we go. That also forms the NC terminal of a peptide. Here we go. Here's one. Here's another example. And here's the review of all of these. Note ionic salts usually contain the metal and the non-metal. So, now the review. The main is to give an elemental force like zinc and terbium. Yeah, the terbium. The green non-metals typically gain electrons, and all the metals tend to lose electrons and chemical electrons. Can you predict a common oxide for these elements? How does a gain or lose election to achieve a noble gas or noble gas like in configuration? I'll give you a few moments to ponder this. Feel free to pause the video. Click. Okay, if you're back, that means you must have solved these. -1 plus 1, -2 plus 2, -4, 2 plus, 3 plus, 4 plus, 2 plus, 3 minus 1 plus 3 plus. When the elements in zinc column moves their 2 at the S election to become 2 plus. Charges are harder to predict over here. So here's your homework. Create 3 compounds. Write its name and the charge you use. Write the formula. Make sure the charge is balanced to make a neutral compound. A compound should contain 1 charged green element, 1 other charged element. Use Wikipedia to learn about what you created. Here's an example. Barium dichloride, 2 plus, -2. Radioactive compounds and their charges. Ooh, sodium was radon. Francium, +1, +2, +3, +4, +5, +6. Do we plus? No, we do not. That should have +4, +3, all the way up to here, +2 and +1. These are harder. Can you create compounds for elements and what are the formula for the polling compounds? Use your imagination. This is very diverse. I'll give you a few moments to ponder these questions. Feel free to pause the video. Click. Well, if you are back, this must mean that you followed the puzzle. Here we are. FrCl, RaO, ACCO3, THO2, PaCl5, UF6. So here we go again. 5, 4, 3. And then here we have the 2. Sodium and nutrition. The sodium chloride is dominant in our cells. The sodium is with first not to neutral sodium metal, Na0, but is an Na plus ion. High sodium diets can lead to high blood pressure, but we do need something to maintain the correct salinity in our blood flow. This sodium diet, Mg, not G, is needed in very small amounts. Mg0 plus HCl. What's going on? Like this. Here we go. And then that's the reaction. See? Because then when this happens, they bond together and that's it. And this is the end. We'll see you later. Don't forget to subscribe. Very important for my channel. And I'll see you later in the next episode. Bye for now.